off or how I determined your grade. Sometimes you can get points back if you just explain to me what you did, because I may not be able to understand what you did, right? All right, so where are we in this class? Are we getting close to a midterm yet? Not really. I think we're still a ways off. Yeah. Yeah, so we still have a ways to go before we have a midterm. Last time, what were we covering? Implicit. Right. We did all the partial, right? All this stuff, partials, and then we moved on to, that was 11.3. We just got through the tangent plane stuff, and I had you do a problem. Where the heck is it? Whoa, why is it so? I had you try this one, right? And then we worked it out, I believe, together. Did we ever get that answer? I don't know if we did. And then that was the end of the section. So do y'all want to start here, or do you want to move on? We can revisit this problem, or we can move on. It's totally up to you.
Can we just recap this real quick?
Yeah? Okay. So recapping. This section was very short, tangent planes. It was how you can find the equation of the plane that is tangent to a surface at a point. So if someone gives you a function, a surface function of two variables, z is some function of two variables, that draws a surface, and then we have some point on that surface. This formula is the formula we can use to find the equation of the plane that is tangent to that surface at that point. So the example that we kind of ended with, and I, again, don't know if we worked this completely out, but we will, is this right here. We're trying to find the equation of the plane that's tangent to that surface at that given point. We did solve it? Y'all still want to see it though? I don't care, it's up to you. Yes or no? Yes?
Yeah.
Okay, I'll do it. So I need the formula first, right? The formula says that to find the equation of this tangent plane, I'm going to take the partial of f with respect to x, evaluate that at x naught, y naught, then multiply that by x minus x naught. This formula I'm just copying from the notes earlier. Plus the partial of f with respect to y, evaluate that at x naught, y naught, and then multiply that times y minus y naught, and then minus 1, and I told you that minus 1 will always be the case for this particular scenario where z is a function of x and y, and then equals 0. And I told you I would explain where this negative 1 comes from later when we generalize this formula. So that's it. We need some partials. So here's our function. Let's take the partial of f with respect to x first. So the derivative of arctangent of anything is 1 over 1 plus whatever was there squared times the derivative of what's inside. Now, when we take the partial with respect to x, what variable are we holding as constant? Y, right? So when we take the derivative of x times y squared, if y squared is a constant, I can kind of ignore it and then say what's the derivative of x with respect to x?
Y squared.
Yes, so the derivative of x would just be 1 and then times the constant. So this would just be y squared here. Y'all got that or no? Yes? Okay, now I'm also going to need the derivative, the partial with respect to y. To do that, same exact story. Derivative arctangent of something is 1 over 1 plus whatever the argument is squared. But now I'm treating x like a constant. So I imagine that that's a constant, and I have to take derivative of constant times y squared, which would just be 2y times that constant. So this should just be x times 2y? Or can I just write 2xy? Is that all right with you? 2xy? That's good? All right, so I need those to now, that was kind of like my work. My derivatives. Now let's go ahead and figure out what this is and what this is. What is x naught, what is y naught, and what is z naught? Do we know? Yeah. This is x naught, this is y naught, this is z naught. Right? So we know what those are. And so now, let me figure out what this is. Right? To figure out what this is, I need to do the partial of f with respect to x, but inside of it, I'm plugging in what? 1, 1. So in here, everywhere you see x, put a 1. Everywhere you see y, put a 1. Can you all see the red okay? Yeah? So 1 times 1 squared is still 1. 1 squared is 1. So the bottom, that's just 1 plus 1. And then times 1 squared. It's pretty easy when it's all 1s, right? It's just a half. Yeah, I remember doing this now. And then when we do the partial with respect to y, this one, we're going to do the partial of f with respect to y at 1, 1. And so plug 1, 1 into that. And I think the only difference we got there turns out to be 1, I think. Yeah. Yeah, this turns out to be 1. And so now you can just plug in to the formula. So I'm ready for my final answer. My final answer should be, remember, this is the equation of the plane. It should be this right here, which we found to be 1/2. In front of x minus x naught was 1. And then plus partial of f with respect to y, evaluated at 1, 1, which was 1. So plus 1, y minus y naught was 1. There's a lot of 1s here. And then minus 1, and then z minus z naught, but z naught was pi over 4. And then all of that equals 0. There you go. You can box that up. That's the equation of the plane. So that's what we ended, I believe, class with last time. Okay? All right, so today what we're going to do, we're moving to the next section. And the next section is 11.5. Where is it? There it is. And I have a different set of notes for this. I don't use the Wolfram for this. All right. So the previous section, not the tangent plane one. Before the tangent plane, we learned about how to find partial derivatives, right? And we also, within taking partial derivatives, we did use chain rule, didn't we? We did, like the problem we just did. We had to do chain rule on that arctangent. This entire section gets into trying to find like a generalization of the chain rule for functions of several variables. So we're going to kind of like really go deep into what chain rule is and how we can adapt it to different functions of more than one variable. So we start chain rule with a discussion about chain rule the way it appeared in Cal 1. So let me just put something on the board here first. Back in Cal 1, right, if you had y equals, let's say, sine of x squared, like that, right? If you were asked to take derivative of that, right, find dy dx, you start with the outer function, right? You take derivative of the outer, which would be cosine of x squared. And then you multiply that times the derivative of the inner function, which would be 2x, right? And we're all hopefully very, very comfortable with that idea, right? What I want you to see here with this chain rule is that the y, right, depends on x, right? We say y is a function of x. In order to know what y is, all I need to know is what x is, right? If somebody gave me a value of x, I could then tell you what y is, right? So y completely depends on the value of x. X is the input, y is the output. So drawing this, we could draw it like this, y, and then below it, x. So this is kind of like the higher up you are, this y looks down to the x to see where it gets its value from, all right? So this would be like a schematic drawing of this situation. Y ultimately depends on x, right? And when we talk about a derivative here, if y depends on x, the only derivative that we could possibly talk about here is the derivative dy dx. Okay, dy dx is the derivative we have. It's the rate of change of y with respect to this variable. Okay, let's continue with the same example. What I'm going to do over here is I'm going to try and show us the chain rule a little bit different. We could say that y here was sine of, let's say, u. And then we could say that u here was x squared. And wouldn't that be the same thing? Like, if I said that this y is sine of u, but then I tell you to replace the u with x squared, this would be the same as these two statements. So when we write dy dx here, the chain rule says this will be dy du times du dx, saying that if we take the derivative of this with respect to u, what's the derivative of this with respect to u? Cosine u, right? Isn't that what this is? Isn't that cosine of u? So this piece right here is dy du times, right, times, and then the dx, the 2x is what? The du, it's the derivative of u with respect to x, which is 2x. So this piece right here is du dx, like that. So this is what chain rule really is in Cal 1, all right? That's just a recap of what it is. Let's move on. So that's just what I just said, okay? This we're not even going to write on the board. I'm just going to talk through it, right? Obviously, y there depends on x. You're back in Cal 1. What's dy dx? 2x plus 6. We're done, right? There's not even any chain rule happening there. It's just a regular old derivative. Y depends on x. Now, what if I tell you that y depends on x and x depends on t? Let me give you the example first. Look at that right there. Y depends on x. Do you all see that? Y depends on x. And x depends on t. Then the picture of this is that y depends on x, but x depends on t, right? So if I know t, I'll know x, but if I know x, I'll know y. So ultimately, y depends on what? One thing, right? Y depends on one thing. So if I want to know what dy dt is, right? If I want to know how much that changes, if I change this a little bit, how much that changes, that's dy dt, then what I'm going to do is I'm going to look at this chain of, this branch, okay? I'm going to look at this branch and I'm going to say from here to here, I have dy dx, right? From here to here. And from here I have dx dt. And so if I want to know dy dt, which is the connection between these two, I'm going to multiply those two together, right? If I multiply this times this, I should get this. So this should be dy dx times dx dt. Let me try and restate this again. This is basically chain rule, right? It's saying that if y depends on x and x depends on t, ultimately y depends on t. So if I want to know the change in y with respect to t, then what I need to do is figure out what the change of y with respect to x is and multiply that times the change of x with respect to t. If I multiply these two together, I have this. So let's do each one of these. What is dy dx? 2x. Times what's dx dt? So what's the derivative of x with respect to t here? Cosine t, right? So that's your answer. But hold on. We need everything to one variable. So here, remember, y depended on t. I want the change in y with respect to t, so I want everything here to have t in it. So I replace x with what? With whatever x is, right? What's x? Sine t. 2 sine t times cosine t. This is dy dt. You all right with that? So a lot of this is stuff we've done already, all right? But we're going to just keep extending it, all right? So I'm going to give you a new example that's not that one. I'm just going to make one up. Oh, shit. Oh, I forgot where I was here. Hold on. I went way too far there. Let me bring up a blank page here. That'll work. So I'm making up this example for you. What if I tell you this? And let's keep it nice. I'll keep it, I won't go too crazy here. Let's say that y is x cubed. Let's say that x is the natural log of t. Let's say that t equals w squared plus 1. Let's go plus w plus 1. Find, well, you tell me what you think I'm going to ask you for. dy dw. dy dw. Because ultimately here, look at the chain of events. Y depends on x depends on t depends on w, right? So ultimately, y first depends on x, but x depends on t, and t depends on w. So if I know w, I'll know t. If I know t, I know x. If I know x, I know y. Yes? So dy dw is this right here, right? That's dy dw. If I change w a little bit, what's the impact on y? That's what this is. To get it, what do? I go down the branch and I multiply each of these derivatives down the branch. So this would be dy dx. This would be dx dt. This would be dt dw, right? See that this is just a visual aid for us? All it is a visual aid. You'll see why the visual aid is useful in a minute. All right, so if I want to know dy dw, I'm going to do dy dx first times dx dt times dt dw. Pardon? Yeah, and so this is why Leibniz notation is nice, is because if you actually cancel those and cancel those, what would you get? dy dw, which makes sense, right? So it's almost like if you're trying to find this, you could rewrite it this way and then just take your derivatives. So it's kind of a nice result of the notation. What's dy dx? 3x squared. Times, what's dx dt? 1 over t. Right, you're taking derivative of natural log. And then times derivative of that, 2w plus 1. I need that in parentheses, don't I? I can't just leave that like that. Okay, now I need all of that in terms of what? W. So let me start with this. What can I replace x with? Natural log of t, so natural log t squared times 1 over, what's t? W squared plus w plus 1. And then times, I still have the 2w plus 1. Almost there. I need to replace this t with w squared plus w plus 1. And then everything will be in terms of w. 3 natural log w squared plus w plus 1. All of that squared times 1 over w squared plus w plus 1. Let me go ahead and take this 2w plus 1 and slide it on top here. There we go. That would be your derivative. Follow? Okay. So far everything's great, right? And you can imagine that I could, if I want next to this, put what? W is equal to some function of some other variable, right? And then we just, our branch would get longer and longer and longer, right? Okay. Now let's look at this. What if I tell you this? What if I tell you z, right? Z equals x squared y Let's just do that. Z is x squared y. So let's try and draw this thing. Z depends on what? X and y, right? You can't just give me x and I know what z is. You just can't give me y and I know what z is. You have to give them both, right? So in order to know z, I need to have two pieces. I need to know x and I have to know y, right? And because I now have two branches, right? I have two branches. I cannot ask you for a single derivative because I have two branches. I can ask you for two different derivatives. The first derivative is a derivative that goes down this branch. And that would be what? Yeah, so this would be the derivative. You're wanting to say this is dz dx, right? But because we have two branches, that means we would have to hold this variable constant and talk about partial derivatives. So down this branch, I say partial of z with respect to x. And down this branch, I say partial of z with respect to y. And so do y'all see that there are two different derivatives that we could possibly ask for here? Where in the previous examples, because we only had one branch, I could ask for only one derivative. It was d whatever top variable over d whatever the bottom variable was at the bottom of the branch. Here there are two different ones. So here, let's figure out what this is. What's this? Well, that's what we did last class, right? What's the partial of z with respect to x? I'm holding y as a constant. Treat y as a constant. 2xy. Right? 2xy. That's one possible derivative I could ask you for, right? Now, let's do the other one. With respect to y. That's the other branch, right? That's now holding x to be constant. And so what would that be? X squared. Just x squared. So if you have a variable that depends on two other variables, right, then you are going to have two different partial derivatives possible. Two of them. One when you hold the x constant, one when you hold the y constant, or the other way around. Good? All right, let me change it a little bit. You ready? Same problem. I'm going to give you that same thing. Starting over, new problem. I'm going to start with that. And I'm going to tell you this now. X is equal to sine t, and y is equal to t to the fifth power. So what do you need in order to know z? X and y, right? What do you need in order to know x? T. What do you need in order to know y? T. So ultimately, to know z, you just need to know t, right? Here's what this picture looks like. Z depends on x and y. But x depends on t, and y depends on t. And so ultimately, z depends on t. You give me t, the t will come in and give you the x and y, which will give you the z. So what derivative is possible for me to ask you? Are there more than one? Is there only one? What is it? What do you, well, there's two branches, right? But they both depend on the same variable, right? So there's only one thing that we can ask for here, and that would be dz dt. How much does z change by if I move t a little bit? And do you see that by me moving t a little bit, z is going to change, right? And I don't have to hold anything constant for that to happen. Right? If I just change the value of t down here, it's going to impact y and then z, yes? How do we find out what this is, though, right? That's the whole question here. This is the big, okay, how do we deal with this? We saw that when the t's weren't here, we had two possible answers, right? Two different partials. But if we only have one possible answer, how do we calculate this?
Do we divide one partial by the other?
Okay, so maybe you divide, right? Maybe you divide. Let's try and draw the branches first. What derivative makes sense from here to here? Partial z with respect to x, right? And then down? dx dt, because that x depends on only one thing. Okay, from here to here is what? Partial z with respect to y, and then from here to here? dy dt, because y only depends on t. You only have partials down your branches if you're holding another variable constant. If that variable depends on only one thing, then it's a regular straight old derivative. So my question again was, what do you think? What is your instinct telling you this answer should be? How is it related to this tree? Any guesses? If it were just that branch, if it were, we would just do that times that, right? Okay, but we have two branches, so what do you think? Is it that times that times that times that? Does that make sense to you? Think it's plus? You think it's that plus that plus that plus that? Or no?
That times that
Plus, that's exactly what it is. You go down each branch and you add them up. Okay, so I'm going to go down this branch first. I get partial z with respect to x times dx dt plus, so I went down this branch, right? And now go down this branch, add to it partial z with respect to y times dy dt. See how that works? It's the sum of the branches going down the branches. And now let's find out what each of these were. What's the partial of z with respect to x? We did that earlier, didn't we? 2xy. Times, what's the partial of x with respect to t? Cosine t. Plus, what's the partial of z with respect to y this time? X squared, we did that earlier, right? Then not partial, derivative of y with respect to t. 5t to the fourth. And now you replace all your x's with what? Sine t, all your y's with t to the fifth. And that final answer will be completely in terms of t. Let me go ahead and write that down. It'll be 2x was sine t, y was t to the fifth, times cosine t, plus x was sine t, but squared, sine squared t, times 5 times t to the fourth. I'm not cleaning that up or anything, I'm just writing it down. That is the derivative of z with respect to t. What we're looking at here is trying to find like a general way to find derivatives of things that depend on maybe more than one variable, and then each of those variables might depend on one or more variables. How do we even talk about derivatives? How do you incorporate the chain rule into something like that? And it's a very visual thing. Questions? All right, can I erase? I'm ready to change the problem. What if I tell you that z is x squared y minus w? I want you to find all derivatives that are possible. Okay, the instructions here would be find all possible derivatives of z. I'll say of z. You have to be a little bit specific here. All derivatives where you have z on top, right? So what is z a function of here? X, so you need to know x, and then you also need to know y, and then you also need to know w, right? Now, these don't depend on anything, right? They don't depend on the same variable. So how would we do this? How many derivatives are possible? 3. There's 3 possible derivatives. They are partial z with respect to x, this one, partial z with respect to y, this one, w, right? Those are the 3, right? There's 3 different ones. And so let's write them down. The first one, partial z with respect to x, that would be what? 2xy minus, well, what's the derivative of w with respect to x? 0, right? So when we're taking derivative of z with respect to x, we're actually holding what constant? Y and w. Y and w are both held constant. The only thing you're treating like a variable is x, all right? So the derivative of this, you're holding y to be constant. Y comes for the ride. Derivative of x squared is 2x. Minus derivative of w with respect to x is 0 because we're holding w constant. Sorry, not 0. W is a constant. Derivative of that 0. What's the partial of z with respect to y? X squared. And finally, what's the partial of z with respect to w? Negative 1. Because this is all a constant now, right? Derivative of that 0, and then derivative of negative w is negative 1. You ready for the next one? Okay, same problem. Okay, same problem. I'm going to throw you into the fire. X is equal to r plus s. Y is equal to r times s cubed. And w is equal to r squared plus s squared. See, we're trying to see, like, how freaking bad can this get, right? Like, how many different variables can you get depending on how many different variables, right? And do we still have a way of talking about derivatives in this case?
Yes.
Yes, we do, all right? So let's see here. Z depends on what? X, Y, and W. Okay, what does X depend on? R and S. What does Y depend on? R and S. What does W depend on? R and S. Okay, let's see what this tree looks like. These are called tree diagrams. Okay, I've been calling these branches. I was kind of waiting to reveal they call these tree diagrams. All right, I'm going to give myself some space. Okay, that's X, right? That's Y. That's W. If I know X, Y, and W, I'll figure out what Z is. To know X, though, I need to know what? R and S. To know Y, I need to know R and S. To know W, I need to know R and S. How many derivatives are possible for me to ask with respect to, or not with respect to, how many derivatives of Z are possible here? What do you think? 3? 6? Well, I agree that there's 3 branches, and I agree that, you go down this branch, there's 2 branches there, and go down this, and there's 2 branches there, 2 branches. I agree with that, but ultimately, what does Z depend on? How many things? 2 different things, right? R and S. So that means there's only 2 derivatives possible. And what are they? It's the partial of Z with respect to R and the partial of Z with respect to S. Those are the only 2 that are possible.